Right now, at this very moment, astronomers around the world are preparing their instruments for something that might happen in the next 24 to 48 hours. Something that could rewrite what we understand about where comets come from and what they're made of. 2 days ago, on October 29th, 2025, at precisely 11:47 UTC, Comet 3I Atlas survived its closest encounter with the Sun, a moment called Perihelion, when it faced temperatures capable of vaporizing rock and tearing apart ice. It survived. That's confirmed. The nucleus stayed intact. The coma persisted. The tail continued streaming away from the solar wind. But here's what nobody can confirm yet, and here's what every major observatory on Earth pointing their equipment toward one specific patch of sky. It might turn blue. Not the pale yellow-white you'd expect from a typical comet. Not the subtle green glow that comes from cyanide radicals breaking apart in sunlight. Blue. Vivid, unmistakable, profound blue. And if this interstellar visitor from beyond our solar system shows us that colour in the coming days, it will answer questions we've been asking since 2017, when we first discovered that objects from other star systems regularly pass through our cosmic neighbourhood. How is that even possible? The comet survived the Sun's brutal radiation. That part is documented, verified, confirmed by multiple observatories tracking its path. What happens next, what we might witness starting November 1st as Earth's viewing geometry, finally allows us to see this object clearly, for the first time in over a week could reveal secrets locked inside its nucleus for billions of years. Secrets about the star system where it formed, the chemical environment that created it, the journey it took across light years of interstellar space to arrive here, now, in our solar system. Amateur astronomers with backyard telescopes might see it first. Professional observatories are scheduling spectroscopic observations. International networks are coordinating data-sharing protocols. The question isn't whether we're watching. Everyone is watching. The question is what we're about to witness. This isn't speculation about aliens or conspiracy theories about hidden government knowledge. This is observable, measurable, scientifically rigorous astronomy happening in real time, and you can participate. The colour of a comet, something as simple and visual as whether it appears blue or white or yellow, carries information encoded at the molecular level, information about carbon chemistry and volatile composition and thermal processing. Blue means something specific in cometary science. It indicates the presence of diatomic carbon molecules and ionized carbon monoxide, species that form when carbon-rich material sublimates and gets hit by solar ultraviolet radiation. Blue tells us the comet came from a stellar environment rich in carbon, possibly from a star system chemically different from our own Sun, possibly from a formation region where planets and comets assembled under different rules than the ones that governed our solar system's birth forepoint X billion years ago. The precedent exists. In 2019, another interstellar visitor designated 2I Borisov passed through our solar system, and astronomers detected enhanced blue emission during and after its perihelion passage. That comet carried carbon-rich material that sublimated as it heated, producing the characteristic blue glow that marked it as compositionally distinct from typical solar system comets. The discovery established that interstellar visitors can show us their origin stories through colour, through the specific wavelengths of light their molecules emit when energized by the Sun, and remarkably, as observations rolled in around October 29-30, initial data from multiple observatories is already confirming this pattern. 3I Atlas is showing signs of blue coloration, precisely what the spectroscopic models predicted. The comet is presenting us with that distinct blue signature. This isn't speculation anymore, this is measured, documented reality. If 3I Atlas continues this pattern, if ongoing observations through November confirm sustained blue coloration like we're already seeing it, would confirm that carbon-rich composition is common among interstellar comets, that they're bringing us samples of stellar chemistry from across the galaxy, that we're living in an era when understanding distant star systems no longer requires travelling to them because they're sending us pieces of themselves. But here's the crucial point. The reason this matters right now in late October 2025, we don't know yet. The observations haven't been made. The spectroscopic data hasn't been collected. For the past 8 days, since October 21st, solar conjunction has blocked Earth's view of the comet. The Sun sat directly between us and 3I Atlas, making ground-based observation impossible, forcing astronomers to wait while the comet completed perihelion and began moving away from the sun's overwhelming glare. That geometric barrier lifts tomorrow, November the 1st. The viewing window opens, telescopes around the world are ready, amateur networks are coordinated, professional observatories have scheduled time on high-resolution spectrographs. The preparation is complete. Now comes the observation. If you want to understand what astronomers are watching for, what specific signs would indicate blue coloration, how this observation connects to larger questions about galactic chemistry and stellar formation, and the frequency of interstellar visitors, then stay with this. Drop a comment. Have you been tracking 3i Atlas since its discovery? What would surprise you most about an interstellar comet changing colour after perihelion? Because in the coming days, observations will determine whether this visitor from another star system is about to teach us something fundamental about how carbon behaves in environments beyond our sun's influence, and you're going to understand exactly what that means, why it matters, and how you could contribute to this moment of cosmic discovery. October 29th, 2025, 11:47 UTC. That's when 3i Atlas reached perihelion, its point of closest approach to the Sun, at a distance of 1.3 from 56 astronomical units, about 203 million kilometers, roughly the orbital distance of Mars. At that location, solar radiation intensity reaches approximately 770 watts per square meter, enough energy to sublimate frozen volatiles, decompose complex organic molecules, and fundamentally alter the surface chemistry of any object passing through. The comet survived. Confirmation arrived through October 30th observations. No fragmentation detected, nucleus structurally intact, coma and tail structures persisting with expected morphology for a post-perihelion comet. The object came through the most intense thermal and radiative environment it will ever experience in our solar system, and it remained whole. But survival isn't the interesting part. Survival was expected based on pre-perihelion brightness curves and spectroscopic observations showing a nucleus large enough and cohesive enough to withstand solar heating. What's interesting happens now, in the days following perihelion, as the comet moves away from maximum solar intensity and enters a phase where different physical processes dominate. The moment of peak heating has passed. Now comes something potentially more revealing, the thermal relaxation phase, when subsurface layers continue warming from conducted heat, even as surface temperatures begin dropping, when volatile species stop sublimating in sequence based on their specific sublimation temperatures, when the comet's composition reveals itself through the changing chemistry of its coma. This is where timing becomes critical. As 3i Atlas moves away from perihelion, it simultaneously emerges from a viewing constraint that's prevented Earth-based observation for over a week. October 21st brought solar conjunction, the geometric alignment where Earth, Sun, and Comet formed a straight line with the Sun positioned directly between us and the target object. That configuration makes ground-based observation essentially impossible because the comet sits within the Sun's overwhelming glare, lost in scattered sunlight and atmospheric distortion. Professional observatories couldn't point their instruments toward it without risking equipment damage from stray solar radiation. Amateur telescopes had no hope of detecting it against the bright sky. For 8 days, from October 21st through October 30th, astronomers could do nothing but wait and calculate and prepare for the moment when geometry would shift enough to permit observation again. That moment arrives November 1st. Solar elongation, the angular separation between the Sun and the comet as viewed from Earth, increases to approximately 18 to 22 degrees, enough separation for ground-based telescopes to distinguish the comet from solar background light, enough for spectroscopic instruments to collect clean data without contamination from scattered sunlight. The observational window opens. This isn't arbitrary timing chosen for dramatic effect. This is orbital mechanics determining when physics permits observation, when the combination of post-perihelion evolution and improved viewing geometry creates optimal conditions for detecting compositional changes. What astronomers expect during this window: evolution of the coma as cooling progresses. Different volatile compounds have different sublimation temperatures, the specific temperature at which solid ice transitions directly to gas without passing through liquid phase. Carbon dioxide sublimates at 194 Kelvin, roughly -79 degrees Celsius. Water ice sublimates at 273 Kelvin, 0 degrees Celsius, the freezing point familiar from everyday experience. As the comet's surface cools post-perihelion, these volatiles stop sublimating in reverse order of their sublimation points. Carbon dioxide production drops before water production. The changing ratio of gas species in the coma alters its optical properties, potentially shifting the dominant colour as different molecules emit light at different characteristic wavelengths. What astronomers are specifically watching for, whether this cooling process reveals carbon-rich species that would produce blue emission. Diatomic carbon, designated C2 in chemical notation, produces distinctive blue emission bands when molecules absorb solar energy and re-emit it as fluorescence. Ionized carbon monoxide, designated CO+, produces violet and blue emission lines when carbon monoxide molecules lose an electron to solar ultraviolet radiation and then emit light as they return to lower energy states. These species, if present in sufficient abundance, would make the comet's coma appear blue to observers using either visual observation through telescopes or photometric measurement through blue wavelength filters. The significance extends beyond simple colour observation. Carbon-rich composition in comets indicates specific formation environments. Our solar system's comets, the objects born in the Sun's protoplanetary disk 4.6 billion years ago, have characteristic carbon-to-oxygen ratios determined by the temperature and pressure conditions, where they condensed from nebular gas. Comets forming closer to the young Sun incorporated different volatile mixtures than those forming farther out. But all of them formed within the same stellar system, governed by the same initial chemistry, constrained by the same elemental abundances present in the solar nebula. Their compositions vary within a specific range defined by solar system conditions. Interstellar comets formed elsewhere. Different star systems have different elemental abundances based on the specific mix of heavy elements present in the molecular cloud that collapsed to form that star, a stellar system born in a region of the galaxy with higher carbon abundance would produce carbon-rich comets. A system formed from gas enriched by previous generations of massive stars that ejected carbon through stellar winds would have different chemistry than our Sun's formation environment. The composition of an interstellar visitor carries a signature, a chemical fingerprint of its origin system's formation conditions. Blue coloration would indicate carbon richness. Carbon richness would suggest formation in an environment different from our solar nebula. Understanding that difference teaches us about stellar diversity across the galaxy. The timeline matters because these observations require specific conditions. November 1st and 2nd represent the first opportunity for ground-based observation with good viewing geometry since before perihelion. Any compositional changes triggered by perihelion heating should be detectable during this window. Amateur astronomers in the Eastern Hemisphere will have first observation opportunities as the comet rises above the horizon after sunset. Western Hemisphere observers follow hours later. Professional observatories distributed globally ensure continuous coverage across Earth's rotation. The coordination is deliberate, planned weeks in advance, designed to maximize data collection during the critical post-perihelion phase. But, and this matters profoundly, observers are preparing, not confirming. The expectation of blue coloration is based on precedent from 2I Borisov, on theoretical understanding of carbon chemistry, on modelling of how interstellar comets might behave under solar heating. It's an educated hypothesis, not a guaranteed prediction. Science works by testing possibilities against observation. November 1st begins that test. The comet will show what it shows. Instruments will record what's actually there. Analysis will interpret measurements. Only then, after observation, after measurement, after careful analysis, will anyone know whether blue appears or whether 3I Atlas reveals different chemistry than expected. The intellectual honesty is crucial here. This isn't building hype for a predetermined outcome. This is explaining what astronomers are watching for and why that observation matters regardless of result. Blue would indicate carbon-rich composition, answering specific questions about interstellar chemistry. No blue would indicate compositional diversity among interstellar visitors, answering different but equally valuable questions about stellar formation environments. Either outcome advances understanding. The process is what matters. Careful observation, rigorous measurement, hypothesis testing through empirical data, and that process begins in hours, as November 1st dawns and the first telescopes point toward the patch of sky where 3i Atlas emerges from conjunction, carrying whatever secrets its nucleus holds about the distant star system where it formed billions of years ago, beginning the journey that brought it here to our solar system, to this moment when humanity first gets the chance to study its post-perihelion evolution and learn what an interstellar visitor looks like when the sun's heat has finished transforming its surface chemistry. The window is opening, the instruments are ready. Now we watch and see what reality reveals, because in science, reality always has the final word, and that word arrives through observation starting tomorrow. Before discussing whether 3i Atlas will display blue coloration, you need to understand what blue would actually mean if it appears, because colour in cometary astronomy isn't decorative or random, it's diagnostic, carrying specific information about molecular composition encoded in the wavelengths of light emitted by different chemical species. Comets produce colour through two primary mechanisms: reflected sunlight scattered by dust particles, and molecular emission where specific molecules absorb solar energy and re-emit it as fluorescence at characteristic wavelengths determined by quantum mechanical energy level transitions. Different molecules produce different colours. The colour you observe tells you which molecules dominate the coma. Standard cometary colours map to specific chemistry. Yellow and white coloration comes primarily from dust, scattering microscopic silicate particles, fragments of rocky material from the nuclear surface, scattering sunlight much like clouds scatter white light to appear white or grey depending on density. This is reflected light, not emission, and it tells you the comet is producing dust faster than pure gas. Green coloration, extremely common in comets, and sometimes so prominent it's visible to naked eye observers, comes from cyanide radical emission designated CN in chemical notation. When cyanide molecules formed from carbon and nitrogen absorb ultraviolet sunlight, electrons jump to higher energy states and then drop back down, emitting green light at wavelengths around 388 nanometers in the process. Nearly every active comet shows some green because cyanide forms readily when organic compounds decompose under solar ultraviolet radiation. Red coloration appears in some comets from diatomic carbon molecules, the same C2 species that can also produce blue, but in different temperature regimes. When diatomic carbon exists at specific temperatures and excitation states, it emits in red wavelengths. The chemistry is complex, involving rotational and vibrational energy states of molecules, but the observable result is straightforward. Red glow indicates carbon-rich material sublimating and emitting in the red portion of the spectrum. This is less common than green, but well documented in comets with high carbon content. Blue and violet coloration represents ionized species, primarily carbon monoxide that's lost an electron through photoionization when high-energy ultraviolet photons from the sun hit neutral carbon monoxide molecules and knock electrons free, creating positively charged CO+ ions. These ions emit light at specific wavelengths in the blue and violet range, particularly strong emission bands around 425 nanometers. Additionally, diatomic carbon C2 produces prominent blue emission bands in certain excitation states. The combination creates the blue coloration observers would see visually through telescopes or measure photometrically using blue wavelength filters. This emission requires specific conditions, abundant carbon-bearing molecules and strong ultraviolet radiation, to ionize them or excite them to fluorescent states. The term blue in cometary observation specifically means emission at wavelengths between approximately 380 and 450 nanometers, the blue portion of visible spectrum. This is measurable through several methods. Narrowband photometry uses filters that transmit only specific wavelength ranges, allowing astronomers to measure brightness in blue wavelengths separately from other colors and calculate color indices that quantify how blue the comet appears compared to other wavelengths. Spectroscopy provides even more detail, spreading light into its component wavelengths and revealing the exact emission lines and molecular bands present, allowing identification of which specific molecules are producing the blue emission. Both techniques work together. Photometry provides rapid measurements from many observers. Spectroscopy provides detailed identification from specialized instruments. Why would blue be significant for 3i Atlas specifically? Because blue emission requires carbon-rich composition, and carbon-rich composition in an interstellar visitor indicates formation conditions different from typical solar system comets. Our solar system's comets show carbon, Certainly organic molecules are ubiquitous in cometary nuclei, but the carbon-to-oxygen ratio and the specific forms carbon takes reflect solar nebula chemistry. Comets formed in our system have predictable ranges of composition, determined by where in the protoplanetary disk they condensed. An interstellar comet from a different stellar system formed under different conditions, potentially with different elemental abundances, different temperature and pressure histories, different chemical pathways for molecule formation. Strong blue emission indicates either high diatomic carbon production from extensive volatile decomposition or strong ionization of abundant carbon monoxide, or both. Either way, it points toward carbon abundance beyond typical solar system levels. This would suggest the star system where 3I Atlas formed had higher carbon content in its formation region, possibly because that star formed from molecular cloud material enriched in carbon by previous stellar generations, possibly because the protoplanetary disk conditions favoured carbon incorporation into solids more efficiently than occurred in our solar nebula, possibly for other reasons astronomers would work to understand through detailed analysis. The point is, blue means carbon-rich, and carbon-rich means compositionally distinct from solar system norms, and that distinction tells us something about stellar diversity across the galaxy. The precedent exists and it's important. 2I Borisov, the second confirmed interstellar visitor discovered in 2019, displayed enhanced blue emission during and after its perihelion passage. Spectroscopic observations clearly identified strong C2 emission bands and evidence of abundant carbon monoxide. The comet's carbon-to-oxygen ratio appeared elevated compared to typical solar system comets. Analysis published in peer-reviewed journals documented this composition and discussed implications for Borisov's formation environment. The discovery established that interstellar comets can indeed carry carbon-rich signatures, distinguishing them from solar system objects. It created expectation, not certainty, but reasonable expectation that other interstellar visitors might show similar characteristics. Could 3I Atlas show comparable blue coloration? The question is genuine, not rhetorical. Pre-perihelion spectroscopy of 3I Atlas detected standard cometary volatiles, carbon dioxide, water ice, and interestingly nickel metal emission, which is somewhat unusual but occasionally seen in comets. Observers also detected weak C2 emission bands, indicating diatomic carbon was already present in small amounts before perihelion. This is suggestive. If carbon-bearing species existed pre-perihelion at low levels, perihelion heating might have released deeper layers containing more carbon-rich material, potentially increasing C2 and CO+ emission post-perihelion to levels where blue coloration becomes prominent. But this remains speculation grounded in precedent and theoretical expectation, not confirmed prediction. It represents what astronomers are watching for based on reasonable scientific reasoning, not what they're guaranteeing will occur. The distinction matters because science operates through hypothesis testing, not fortune-telling. The hypothesis, 3I Atlas might show enhanced blue emission post-perihelion, similar to 2I Borisov if it shares similar carbon-rich composition. The test, observe the comet November 1st onward and measure actual emission spectrum. The result will either support or refute the hypothesis, and either outcome provides valuable information. How would blue be detected if it appears? Multiple observational approaches provide complementary data. Visual observers using telescopes might notice the coma appears bluish, rather than the typical yellow-white or green, though this subjective assessment varies based on individual colour perception and observing conditions. More reliably, amateur astronomers equipped with photometric systems can measure brightness through blue filters, typically centered around 430 nanometer wavelengths, and compare to measurements through other filters. If the blue filter magnitude is brighter than expected relative to other colors, it indicates enhanced blue emission. This technique, called multicolor photometry, provides quantitative data that many observers can collect and report to coordination centers. Professional spectroscopy offers definitive identification. High-resolution spectrographs attached to large telescopes can resolve individual emission lines and molecular bands, creating a detailed fingerprint showing exactly which molecules are present and how abundant they are. CO+ produces distinctive emission lines that are unmistakable once identified. C2 creates specific molecular band structures in blue wavelengths that spectroscopy clearly reveals. If blue coloration appears, spectroscopy will identify its source precisely. confirming whether it comes from the expected carbon-bearing species or from some other unexpected chemistry. Comparison between pre-perihelion and post-perihelion observations provides the most powerful analysis. Astronomers collected baseline spectroscopy through October 30th, showing the comet's composition before the viewing gap. November 1st and subsequent observations will show composition after the gap, after perihelion heating has potentially altered surface chemistry. Comparing these datasets reveals changes whether new emission lines appeared, whether existing emissions strengthened, whether color indices shifted. This temporal analysis distinguishes between stable composition and evolving chemistry responding to solar heating. The scientific value is substantial regardless of outcome. If blue appears, it confirms carbon-rich composition, validates comparisons to 2I Borisov, suggests interstellar visitors might preferentially come from carbon-enriched stellar systems, and provides data for refining models of cometary thermal evolution and volatile chemistry. If blue doesn't appear, it demonstrates compositional diversity among interstellar objects, indicates 3I Atlas formed under different conditions than Borisov, challenges assumptions about universal characteristics of interstellar comets, and highlights the importance of studying each visitor individually rather than assuming all will behave similarly. Either way, November observations answer real questions. This is the essence of observational astronomy, letting reality determine conclusions through careful measurement rather than assuming outcomes based on prior expectation. The instruments are prepared to detect blue if it exists. They're equally prepared to measure whatever actually appears. The comet itself will determine which result emerges, and astronomers will record and analyze what the universe reveals through this opportunity to study an interstellar visitor at a crucial phase in its solar system passage. That opportunity arrives tomorrow, as the observational window opens and the first data begins flowing from telescopes around the world, starting the process of discovery that transforms speculation into knowledge through the rigorous discipline of measurement and analysis. To recognize change, you need baseline, a reference point showing what existed before transformation occurred. For 3I Atlas, baseline comes from observations conducted between July and October 2025, the months when professional observatories and amateur astronomers worldwide tracked this interstellar visitor as it approached perihelion. This pre-perihelion data establishes what the comet looked like, how it behaved, what composition it displayed before experiencing maximum solar heating. Understanding this baseline makes November observations interpretable, because comparison reveals whether perihelion altered the comet's characteristics or whether it emerged unchanged from its closest solar encounter. Compositional analysis from pre-perihelion spectroscopy identified several key species. Carbon dioxide appeared prominently in infrared spectroscopy, indicating frozen CO2 ice sublimating from the nuclear surface as solar heating increased during the comet's approach. This is common in comets. Carbon dioxide volatilizes more easily than water ice due to its lower sublimation temperature, so it appears first as comets approach the Sun. Water ice was confirmed through multiple spectroscopic detections, showing the nucleus contains substantial H2O frozen into its structure, likely mixed with other volatiles and rocky material in the complex architecture of cometary nuclei. The presence of both CO2 and H2O indicates the comet formed in a cold environment where these volatiles could condense, consistent with formation in the outer regions of a protoplanetary disk. Interestingly, spectroscopy also detected nickel emission neutral metal atoms that sublimate directly from solid state when temperatures reach levels sufficient to vaporize metallic material embedded in the nucleus. Nickel detection in comets is somewhat unusual, not because comets lack metals, but because detecting metal emission requires specific observing conditions and sufficient sublimation rates. The presence of nickel doesn't fundamentally change interpretations of cometary composition, but it adds detail to the inventory of elements present. Some research suggests metal detections might correlate with compositional properties, though this remains an active area of investigation. More relevant to potential blue coloration, weak C2 emission bands appeared in some pre-perihelion spectra, diatomic carbon at low levels, producing faint molecular fluorescence detectable by sensitive instruments, but not dominant enough to create obvious blue coloration visible to observers. This detection is significant because it establishes that carbon-bearing species were already present before perihelion, creating the possibility that increased solar heating could enhance their production, strengthening the C2 emission to levels where blue becomes prominent. The pre-perihelion detection doesn't predict blue will appear post-perihelion, but it establishes that precursor chemistry exists. Cyanide radical CN was also weakly detected, accounting for the subtle greenish tint sometimes reported by visual observers. This is standard cometary chemistry. CN forms redly when ultraviolet radiation breaks apart more complex organic molecules in the coma. Nearly every active comet shows CN emission. The weakness of CN in 3I Atlas's perihelion spectrum doesn't indicate unusual chemistry. It simply reflects the comet's distance and activity level at that phase of its orbit. Visual appearance through pre-perihelion showed typical cometary structure. The coma, the cloud of gas and dust surrounding the nucleus, appeared yellow-white to most observers, indicating dust scattering dominated visual appearance over molecular emission. Dust production consistent with volatile sublimation created a diffuse coma expanding away from the nucleus as solar wind and radiation pressure pushed material outward. The tail, oriented antisolar as expected from radiation pressure physics, showed standard morphology for an active comet near perihelion. No fragmentation was detected, no unusual jets or asymmetries that would indicate unstable nucleus structure. The object behaved like a comet sublimating volatiles, producing dust, developing tail structure in ways that matched expectations for an icy body approaching the Sun. Activity levels evolved according to predictable patterns. Brightness increased as the comet approached perihelion, following a power law relationship where magnitude decreases, meaning brightness increases because astronomical magnitude runs backwards, proportional to some power of decreasing solar distance. Astronomers use brightness curves to infer activity patterns and sometimes to predict nucleus properties. 3. Atlas's brightness evolution looked normal for a comet of its size and composition approaching the Sun. No dramatic outbursts occurred, no sudden brightness jumps indicating major fragmentation or exposure of highly volatile material. The smooth brightness curve suggested a relatively homogeneous nucleus, responding predictably to solar heating. Trajectory refinement through this period incorporated non-gravitational forces. Comets don't follow perfect gravitational orbits because asymmetric outgassing creates jet thrust that slightly alters their path. As volatiles sublimate preferentially from the sun-facing hemisphere, and as nucleus rotation carries active regions through day-night cycles, gas jets push the nucleus in specific directions, accelerating or decelerating it in ways that perturb the orbit. Astronomers measure these perturbations through careful position measurements over time, then model the forces causing them. For 3I Atlas, non-gravitational forces were detectable and consistent with outgassing patterns, providing additional confirmation that this object behaves like a typical comet physically, even if its origin is exotic. Rotation period remained, uncertain through pre-perihelion observations. Determining rotation requires detecting periodic variations in brightness or spectroscopic features as the nucleus spins and presents different surface areas to observers. For 3I Atlas, light curve measurements showed variations suggesting rotation, but not clearly enough to definitively measure the period. The nucleus might have complex shape creating irregular brightness variations, or the rotation period might be long enough that insufficient time elapsed for multiple rotations to be observed clearly. This is common in cometary astronomy. Rotation periods often remain uncertain until extensive observation campaigns accumulate sufficient data. The inability to measure rotation per perihelion doesn't indicate anything unusual. It simply reflects observational challenges. This is the established baseline as of October 30th, 2025. Everything described here comes from confirmed observations documented in astronomical databases and discussed in community communications among researchers tracking 3I Atlas. This isn't speculation or expectation. This is measured reality, the foundation upon which November observations build. Now consider what perihelion heating potentially changed. Maximum solar flux at 1.356 AU distance delivered approximately 770 watts per square meter to the nucleus surface, intense enough to sublimate volatiles rapidly, to decompose organic molecules through thermal stress, to potentially crack surface layers and expose deeper material. But heat doesn't affect only the surface. Thermal energy conducts inward, penetrating into subsurface layers through the complex porous structure of cometary material. The depth of heat penetration depends on thermal conductivity, which remains poorly constrained for cometary material, but estimates suggest 1 to 2 meters of penetration are possible during perihelion passage. This subsurface heating matters because cometary nuclei aren't homogeneous. They're layered, stratified structures built through complex accretion processes during their formation billions of years ago. Different layers might contain different volatile mixtures, different dust-to-ice ratios, different organic compositions. Surface layers, modified by previous solar passages if the comet entered the inner solar system before or by cosmic ray exposure during billions of years in interstellar space, might differ significantly from pristine deeper layers that haven't experienced processing. Perihelion heating could release material from these deeper layers, exposing composition that wasn't visible during pre-perihelion observations, when only surface material sublimated. Additionally, nucleus rotation during perihelion means different surface regions experience peak heating at different times. If the nucleus has irregular shape with distinct active regions, areas where volatiles sublimate more readily, due to composition or physical structure, then rotation carries these regions through day-night cycles where solar heating varies dramatically. Some regions might reach higher temperatures than others, some might release specific volatile species preferentially. Post-perihelion observations would integrate emission from all these regions, potentially showing composition that wasn't apparent when only certain areas were actively sublimating pre-perihelion. Chemical decomposition adds another layer of possibility. Complex organic molecules, long carbon chains, aromatic rings, heterocyclic compounds containing nitrogen or oxygen can thermally decompose under extreme heating, breaking apart into smaller fragments. If the nucleus contains complex organics built during its formation or subsequently modified by radiation exposure, perihelion temperatures might decompose these molecules, releasing simpler carbon-bearing species like CO, C2, and various carbon-containing radicals. The fragments would sublimate and contribute to coma composition, potentially altering emission spectra in ways that weren't predictable from pre-perihelion observations. Any or all of these mechanisms, subsurface release, rotational exposure, thermal decomposition, could produce post-perihelion compositional changes detectable in November observations. But whether they actually do produce observable changes remains unknown until measurements are made. This is where the November 1st observation window becomes critical. The comet has experienced perihelion. Thermal processing has occurred. Now observations will reveal whether that processing altered observable composition, or whether the comet's chemistry remains stable through perihelion, unchanged in ways detectable through spectroscopy and photometry. The uncertainty isn't confusion or lack of scientific rigor. It's the fundamental nature of observational science testing hypotheses against reality. Theory predicts possibilities. Models estimate outcomes. But actual observation determines what exists. November 1st begins that determination for 3 I-atlases post-perihelion state, comparing what the comet shows now against the baseline established through months of pre-perihelion tracking. The baseline is solid. The theories are reasonable. Now comes the test, when instruments point skyward and start collecting the data that transforms possibility into confirmed knowledge about this interstellar visitor's composition and behavior through its closest encounter with our Sun. November 1st, 2025 represents transition from preparation to execution, from expectation to measurement, from hypothesis to test. The date isn't arbitrary or chosen for dramatic timing. It emerges from orbital mechanics and observational geometry, from the simple fact that Earth, Sun, and Comet move according to physics that determines when observation becomes possible after the constraint of solar conjunction. October 21st brought alignment that blocked Earth's view. November 1st brings separation sufficient to permit ground-based telescopes unobstructed observation of the comet emerging from perihelion. This is the critical window, the period when post-perihelion composition becomes measurable, when any color changes triggered by solar heating become detectable, when months of planning and preparation convert into actual data collection. The geometry matters in specific ways. Solar elongation, the angular distance between the Sun and the comet as seen from Earth, increases through late October and reaches approximately 18 to 22 degrees by November 1st. This separation is sufficient to distinguish the comet from scattered sunlight in Earth's atmosphere and from the bright sky background near the Sun. Professional telescopes can point toward the comet without risking instrumental damage from stray solar radiation. Atmospheric extinction, the absorption and scattering of light as it passes through Earth's atmosphere, decreases significantly at larger elongations, allowing more comet light to reach ground-based detectors. Blue wavelengths, which scatter more readily than red wavelengths through atmospheric molecules, become more transmissible at these viewing angles. If blue emission exists in the comet's spectrum, November 1st, geometry provides better conditions for detecting it than earlier periods when smaller elongation made observation difficult or impossible. Professional observatories worldwide have scheduled observations during this window. The process began weeks ago as astronomers submitted proposals to telescope allocation committees requesting specific amounts of observing time on specific instruments. For 3i Atlas post-Perihelion study, these requests prioritize spectroscopy spreading comet light into detailed spectra, showing emission lines and molecular bands that identify chemical species, and multi-wavelength photometry, measuring brightness through different color filters to quantify color indices. Approval came based on scientific merit, on the recognition that interstellar visitors represent rare opportunities for studying material from beyond the solar system, on the time-sensitive nature of post-Perihelion observations when thermal evolution proceeds most rapidly. The instruments preparing to observe include high-resolution spectrographs capable of resolving narrow emission lines, critical for distinguishing between different molecular species that might emit at similar wavelengths. Medium-resolution spectrographs provide faster data collection with slightly less detail, useful for tracking how spectra change over hours or days. Photometric systems with narrowband filters isolate specific wavelength ranges, allowing measurements of brightness in blue, green, red, and other colors separately. CCD cameras optimized for low-light detection capture images showing coma morphology and tail structure while simultaneously recording brightness information. Each instrument contributes different data, and combining observations from multiple facilities creates comprehensive understanding impossible from any single measurement. Amateur astronomy networks coordinate parallel observations. Distributed around the globe, amateur observers provide geographic coverage that professional facilities cannot match. When the comet is visible from Asia, American professional telescopes can't observe it. Earth's rotation has placed them in daylight. Amateur observers in Asia fill that gap. Hours later, when American facilities can observe, European amateurs contribute their data. This continuous coverage captures temporal evolution, detecting changes that might occur over hours that would be missed by intermittent professional observations. Amateur photometry, collected through standardized methods and reported to coordination centers like the AAVSO or ICQ, provides valuable long-term monitoring complementing the detailed spectroscopy from professional instruments. The timeline unfolds according to Earth's rotation and the comet's position in the sky. November the 1st, approximately 12 fans to 80 Knolls UTC, brings the comet above the horizon for Eastern Hemisphere observatories as evening-twilight transitions to darkness. First observations come from Asia and the Middle East, from amateur astronomers with modest telescopes and professional facilities with large aperture instruments. Initial data flows into online coordination systems where researchers monitor results in near real time, watching for any indications of unexpected behavior or compositional changes. These first measurements establish the immediate post-conjunction appearance, creating a new baseline for comparison. As Earth rotates, the observation window shifts westward. By 23 UTC and through November 2nd, Western Hemisphere observers North and South America gain access as their sky darkens, and the comet rises above their horizon. Professional observatories in Chile, particularly valuable for Southern Hemisphere coverage and excellent atmospheric conditions at high-altitude sites, conduct scheduled spectroscopic observations. North American amateur networks contribute visual observations, photometry, imaging. The global coordination means someone, somewhere is always observing when the comet is observable from any location on Earth. November the 2nd provides a complete day of global observation, with data accumulation across time zones ensuring comprehensive coverage. By November 3rd, preliminary datasets exist spectroscopic measurements from multiple professional observatories, photometric data from dozens or hundreds of amateur observers, visual descriptions from experienced comet watchers, images showing coma and tail structure. Analysis begins, comparing observations to pre-perihelion baseline, searching for signs of compositional change, measuring colour indices to quantify any shift toward blue or other wavelengths, identifying emission lines in spectra to determine which molecules dominate post-perihelion chemistry. What could these observations reveal? Several. Scenarios are possible, each with different implications for understanding 3I Atlas's composition and thermal evolution. In the first scenario, no significant colour change appears. Spectroscopy shows similar emission lines to pre-perihelion observations. The comet remains dominated by dust scattering, producing yellow-white visual appearance. Blue filter photometry indicates no enhancement of blue wavelengths relative to other colours. This outcome would suggest the nucleus composition didn't change dramatically due to perihelion heating, that surface and shallow subsurface layers accessible to volatile sublimation maintain stable chemistry, that carbon-rich species remain weak or absent even after maximum solar energy input. Scientifically, this tells us 3I Atlas differs from 2I Borisov in composition, that interstellar comets aren't uniformly carbon-rich, that each visitor must be studied individually rather than assumed to share characteristics. In the second scenario, enhanced blue coloration becomes evident. Visual observers report bluish tint not present in pre-perihelion observations. Spectroscopy reveals strengthened C2 molecular bands in blue wavelengths, and prominent CO+ emission lines indicating significant ionization of carbon monoxide. Blue filter photometry shows increased flux relative to baseline measurements. The coma's integrated colour index shifts measurably toward blue. This outcome confirms carbon-rich species became more abundant post-perihelion, validating thermal release models suggesting subsurface material or thermal decomposition products emerged after peak heating. It aligns 3I Atlas with 2I Borisov's pattern, suggesting carbon-rich composition might indeed be common among interstellar visitors, supporting hypotheses about their formation in carbon-enriched stellar environments. A third scenario involves intermediate changes, partial blue coloration, mixed with persistent dust emission, spectroscopy showing enhanced carbon species, but not overwhelming dominance, colour indices shifting, but not dramatically. This mixed signature could indicate dynamic evolution in progress, with composition changing over the November 12th observation window as thermal effects propagate through subsurface layers and different regions of the nucleus respond to heating on different timescales. Time-resolved observations during this scenario become particularly valuable, capturing real-time chemical evolution impossible to study except during these brief post-perihelion windows when comets transform most rapidly. Crucially, scientists won't know which scenario represents reality until observations actually occur. All the preparation, all the scheduled telescope time, all the coordinated amateur networks these establish capacity to detect whatever the comet actually shows. They don't predetermine outcomes. The comet itself determines outcomes through its actual physical and chemical state post-perihelion. Instruments record that state. Analysts interpret measurements. Only then, after data collection and careful analysis checking for instrumental effects and atmospheric interference, and all the technical details that ensure measurements reflect reality rather than artifacts, only then does anyone know whether blue appeared, whether composition changed, whether 3I Atlas revealed carbon-rich chemistry, or maintained stable composition through perihelion. This uncertainty represents the core of scientific method. Observation tests theory. Data determines conclusions. November 12th provides the observation opportunity. The coming days will generate data. Analysis over subsequent weeks will extract understanding. The process is rigorous, methodical, designed to eliminate bias and ensure conclusions follow from measurements rather than expectations. Astronomers prepared for multiple possible outcomes precisely because science works by discovering what is, not by confirming what's expected. The data collected during this critical window will definitively answer, does 3I Atlas show carbon-rich composition through enhanced blue emission post-perihelion? The answer matters for understanding interstellar comets, for characterizing the diversity of visitors from other stellar systems, for refining models of how comets respond to solar heating, for testing whether carbon enrichment patterns observed in 2I Borisov represent a common trait or an individual characteristic. Either answer advances knowledge. Both possibilities receive equal preparedness. The instruments stand ready to measure whatever reality presents, and within days, that measurement will replace speculation with confirmed observation, transforming the question of 3I Atlas's post-Perihelion colour from hypothesis into documented fact, recorded in astronomical databases and eventually published in peer-reviewed journals that become permanent scientific record of this interstellar visitor's journey through our solar system. If November observations detect enhanced blue emission, and this remains conditional on actual measurements not yet made, the implications extend far beyond simple colour description. Blue in a comet's spectrum means something specific at the molecular level. It indicates presence of carbon-bearing species in particular ionization and excitation states. And because those species require specific conditions to form and specific compositions to be abundant, detecting blue emission becomes a window into the comet's origin story, revealing information about the stellar environment where it formed billions of years ago before beginning the interstellar journey that brought it to our solar system. The direct chemical interpretation is straightforward. Blue emission around 410 to 430 nanometer wavelengths comes primarily from two sources. Diatomic carbon molecules, designated C2 in chemical nomenclature, produce characteristic emission bands in this wavelength range when they absorb solar ultraviolet photons and remit energy as fluorescence. The process involves complex quantum mechanics electrons in the C2 molecule jumping between energy levels, creating specific patterns of emission lines grouped into molecular bands, but the observable result is blue light. Ionized carbon monoxide, written CO+, produces complementary emission through a different mechanism involving electronic transitions in the ionized molecule. Both species require carbon to be abundant enough that these particular molecular forms reach concentrations high enough to produce observable emission detectable by telescopes. For typical solar system comets, carbon exists but doesn't dominate. The elemental composition of cometary nuclei reflects the composition of the solar nebula, the disk of gas and dust that surrounded the young Sun 4.6 billion years ago when planets and comets formed. That nebula had specific elemental abundances determined by the mix of hydrogen, helium, and heavier elements present in the molecular cloud that collapsed to form the solar system. Carbon was present at levels typical for stellar systems formed from interstellar medium with standard galactic chemical composition. Oxygen was also present at comparable or slightly higher abundance. The carbon-to-oxygen ratio in the solar nebula produced comets where oxygen-bearing molecules, water ice predominantly, but also carbon dioxide and carbon monoxide use up most of the available carbon through chemical bonds, leaving less carbon available for species like C2 that produce blue emission. Comets that show strong blue emission have different chemistry. They contain carbon in excess of what oxygen can bind into typical volatile molecules. That excess carbon forms diatomic carbon molecules, elemental carbon grains, carbon-rich organic compounds that decompose under solar heating to release C2 and other carbon fragments. The elevated carbon abundance relative to oxygen creates the carbon-rich signature observable as blue emission. This compositional difference indicates formation conditions different from the solar nebula. Either the source stellar system had higher carbon elemental abundance, or the formation process incorporated carbon more efficiently, or both. Where do carbon-rich environments exist in the galaxy? Several stellar and circumstellar contexts produce elevated carbon abundances. Carbon stars, late-stage evolved stars that have dredged up carbon from fusion processes in their cores to their surfaces, eject carbon-rich material through stellar winds and eventually through planetary nebulae when they die. Material in the vicinity of these stars becomes enriched in carbon beyond typical galactic ratios. If a planetary system formed from gas contaminated by carbon star ejecta, the resulting comets could inherit carbon-rich composition. Wolf-Rayet stars, massive stars in late evolutionary stages with powerful winds, also eject carbon depending on their specific subtype. Protoplanetary disks around young stars forming in regions where previous generations of massive stars have enriched the local interstellar medium with carbon through supernova explosions and stellar winds might incorporate that enrichment into the solids that eventually form comets. The galactic context matters too. Different regions of the Milky Way have different chemical enrichment histories. The galactic thick disk, an older population of stars orbiting with higher velocity dispersion than the thin disk where our Sun resides, formed when the galaxy was younger and less chemically enriched by stellar nucleosynthesis. Some thick disk environments might have different carbon-to-oxygen ratios than the thin disk where the solar system formed. Comets originating from stellar systems in the thick disk could carry those chemical signatures. The galactic halo, the diffuse outer region of the galaxy containing the oldest stars, represents an even more primordial composition. Though stellar systems there are rare and metal-poor. If 3I Atlas shows strong blue emission indicating carbon-rich composition, astronomers would interpret this as evidence that the comet's source star system had elevated carbon relative to our solar system's formation environment. The specific carbon-to-oxygen ratio measurable through detailed spectroscopy would constrain models of that system's chemistry. Comparing to 2I Borisov's measured composition would reveal whether both interstellar visitors share similar carbon enrichment, suggesting they might originate from similar types of stellar systems, or whether they differ, indicating diverse origins. Over time, as more interstellar comets are discovered and studied, patterns could emerge connecting composition to origin scenarios, building a taxonomy of interstellar visitors based on their chemistry. The profound implication is that colour becomes messenger. Blue light emitted by carbon molecules travelled from the comet to telescopes on Earth, carrying information about stellar chemistry from another star system. That information encoded in wavelength and emission line ratios allows astronomers to read the comet's composition without capturing samples and returning them to laboratories. Spectroscopy at a distance reveals chemical content through the light those chemicals emit. It's remote sensing at the most fundamental level, identifying elements and molecules through their quantum mechanical emission signatures. Consider the alternative. If November observations show no enhanced blue, if the comet's emission spectrum remains similar to pre-perihelion measurements without significant strengthening of carbon species, then 3I Atlas is not particularly carbon-rich compared to solar system comets. This would indicate its origin star system had chemistry more similar to our solar nebula, or that the specific formation location within that system didn't favour carbon incorporation the way 2I Borisov's formation did. This outcome would be equally scientifically valuable because it demonstrates compositional diversity among interstellar visitors. Not all comets from other stellar systems are carbon-rich. Some resemble solar system comets more closely in composition. Understanding this diversity informs theories about planetary system formation, about the range of chemical environments where comets form, about whether our solar system's chemistry is typical or unusual compared to the galactic population of stellar systems. Either result blue, indicating carbon-rich composition, or lack of blue, indicating solar system-like composition, answers scientific questions. The research value doesn't depend on confirming a specific expected outcome. It depends on making accurate measurements that constrain models of interstellar object composition. November observations will provide those measurements. Subsequent analysis will extract compositional information. The result will feed into broader understanding of how stellar systems form, how comets incorporate elements during their birth, how we can characterize visitors from across the galaxy through the light they emit when our sun temporarily warms them during their passage through the inner solar system. This is what makes astronomy powerful. Stars are too distant to visit directly. Exoplanets' planets around other stars can't be sampled with current technology. But occasionally, those distant systems send us pieces of themselves in the form of interstellar objects passing through our solar neighbourhood. When we study those visitors carefully, measuring their composition through spectroscopy, we learn about their origin environments without travelling there. We read messages written in carbon emission and molecular bands and elemental abundances. Blue coloration, if it appears, is one such message. It says, "I formed where carbon was abundant." No blue says, "My formation environment was different, possibly similar to yours." Both messages are worth receiving, worth decoding, worth incorporating into humanity's growing understanding of the galaxy we inhabit. November 12th begins that decoding process for 3I Atlas, when the first spectroscopic observations emerge from conjunction and reveal what this particular interstellar visitor looks like post-perihelion, what composition it carries, what message about its origin it brings encoded in the wavelengths of light emitted by molecules sublimating from its nucleus under the sun's heat. Molecules that formed in a stellar system we'll likely never visit, but can nevertheless study through the chemistry they reveal when warmed by our star during their brief passage through our cosmic neighbourhood. If blue coloration appears in November observations, if 3I Atlas reveals the carbon-rich signature that astronomers are watching for, then observers worldwide will want to participate in tracking this rare phenomenon. Even if blue doesn't appear, Observing an interstellar visitor during its post-perihelion evolution provides valuable experience and contributes to scientific understanding through distributed observations that professional facilities alone cannot achieve. Here's practical guidance for what equipment allows observation, where to find the comet in the sky, what to look for, and how to report measurements that contribute to the collective dataset documenting this object's passage through our solar system. Equipment requirements depend on observational goals. For naked-eye observation, the reality is sobering. 3i Atlas likely remains too faint for unaided eye detection. Current magnitude estimates place it around 11th to 12th magnitude, several times fainter than the dimmest stars visible to humans under perfect dark sky conditions. Naked-eye visibility requires magnitude brighter than approximately 6th, maybe 7th for observers with exceptional vision under pristine skies. The comet doesn't reach that brightness during its current apparition. Attempting naked-eye observation will likely result in not seeing anything, which can be frustrating and discouraging. If unexpected brightening occurs possible but not predicted, then naked-eye observation becomes feasible, but assuming current brightness levels, binoculars or telescopes are mandatory. Binoculars provide entry-level capability. Standard 10x50 binoculars, probably the most common type owned by casual astronomers and widely available at modest cost, can detect objects down to approximately 10th magnitude under reasonably dark skies. This places 3i Atlas near the threshold of detection for binocular observers. Success requires dark skies away from urban light pollution, clear weather without haze or cloud, proper dark adaptation by avoiding bright lights for 20 to 30 minutes before observing, and knowing exactly where in the sky to look. Even meeting all these conditions, the comet appears faint, a dim fuzzy spot indistinguishable from faint galaxies or nebulae, without careful comparison to star charts confirming position. Binocular observation is possible but challenging, best suited for experienced observers familiar with detecting faint objects through binoculars. Telescopes offer better capability. An 8 to 10-inch aperture telescope, reflecting or refracting type both work, provides sufficient light gathering to show the comet clearly as a diffuse object distinct from background stars. 6-inch telescopes can work but require darker skies and more experienced observers. Larger apertures naturally perform better, making the comet easier to locate and showing more coma detail. Magnification matters less than aperture for comet observation. Low-power eyepieces in the 20 to 40 times magnification range work best, because they provide wider fields of view, making it easier to locate the comet, and they produce brighter images of diffuse objects compared to high magnification eyepieces that spread the comet's light over larger areas of the visual field. For observers, specifically interested in detecting potential blue coloration, adding a blue filter enhances sensitivity to blue wavelengths while suppressing other colors. These filters, designated by wavelength range typically 410 to 430 nanometers for blue filters, screw onto eyepieces or camera adapters. Observing through a blue filter and comparing to unfiltered view, or to views through other color filters provides qualitative sense of whether blue emission dominates the comet's spectrum. If the comet appears brighter or more prominent through the blue filter than through red or green filters, it indicates enhanced blue emission. This technique doesn't provide quantitative measurements, but does allow visual observers to detect color shifts that might not be obvious in unfiltered observation, where all wavelengths combine. Astrophotography and photometry require additional equipment. DSLR cameras or dedicated astronomical CCD cameras attached to telescopes through appropriate adapters enable imaging that captures more detail than visual observation and creates permanent records. Photometry, quantitative measurement of brightness, requires calibrated systems where images through different color filters can be analyzed using software that measures star brightnesses and compares them to established standards, allowing calculation of accurate magnitudes. Amateur photometry has become sophisticated, with standardized filter sets, calibration procedures, and software tools enabling amateurs to produce measurements of quality, approaching professional standards. For 3i Atlas observation, photometric measurements through blue, green, and red filters provide data that coordination centers aggregate to track brightness evolution and color changes. Spectroscopy represents the highest level of amateur capability. Small grating spectrographs designed for amateur use attached to telescopes and spread comet light into spectra showing emission lines. These instruments cost more than simple photometric systems and require more technical skill to operate and analyze data, but they provide direct detection of molecular species through their emission line fingerprints. Amateur spectroscopy has contributed significantly to cometary science, particularly for bright comets, where sufficient light enables high signal tonnage measurements. For a faint object like 3I Atlas, amateur spectroscopy challenges even experienced observers, but those with suitable equipment and dark skies can attempt measurements that directly detect C2 and CO+ emission if those species are present at observable levels. Finding the comet requires accurate position information. Ephemerides tables, or calculable predictions of celestial object positions, are available from multiple sources. The Minor Planet Center maintains authoritative orbit determinations and provides ephemeris generation tools on their website. NASA's Horizon system offers highly flexible ephemeris calculation, allowing users to specify observing location, time range, and output format. Free planetarium software like Stellarium incorporates orbital elements for known comets and asteroids, displaying their positions on simulated sky maps that update in real time as users change date and location. Astronomical societies and amateur coordination groups often publish finder charts, showing the comet's path against background stars for upcoming observation periods. For November 12th specifically, the comet emerges from solar conjunction positioned low in the western sky at sunset and dusk. The exact altitude and azimuth depend on observer latitude. Equatorial observers see different sky positions than mid-latitude or high-latitude observers. Consulting ephemeris for specific location provides precise coordinates. The visibility window is initially short, perhaps 30 to 60 minutes after sunset before the comet sets below the horizon, expanding to longer visibility periods as days pass and the comet's angular separation from the Sun increases. Planning observation times using ephemeris ensures arriving at observing site when the comet is above horizon and skies dark enough for detection. What to look for during observation focuses on several aspects. Colour is primary interest given this script's focus. Does the coma appear bluish, or does it remain yellow-white as typical for dust-dominated comets? Visual colour perception is subjective and varies between observers, so qualitative descriptions like appeared slightly blue or no blue tint visible provide more useful information than claiming precise colour measurements from visual observation alone. Using filters provides more objective comparison. Brightness relative to nearby stars of known magnitude estimates how bright the comet appears, contributing to long-term monitoring of activity evolution. Coma size and morphology, whether the coma appears symmetric or shows jets or asymmetries, whether it's sharply defined or diffuse, reveals information about outgassing patterns. Tail structure, orientation, and length document how solar wind and radiation pressure shape material leaving the nucleus. Reporting observations contributes to scientific datasets. Several international databases accept and coordinate amateur observations. The American Association of Variable Star Observers operates a cometry section, collecting brightness estimates and photometric measurements. The International Comet Quarterly compiles observations from worldwide amateurs and professionals, publishing analyses in their journal. The Minor Planet Center accepts astrometric positions, precise measurements of the comet's location, against background stars that improve orbit determination. Online coordination through social media platforms and dedicated forums enables rapid sharing of observations, with hashtags like 3Atlas, facilitating discovery of recent reports. Useful information to include in reports covers date and time in universal time coordinated format, observer location by latitude and longitude or nearest city, equipment used including telescope aperture and type, eyepiece or camera details, filters if any, sky conditions including transparency and light pollution level, brightness estimate or measured magnitude, color description if visual observation, any notable morphological features observed, and observer name and contact information. Standardized formats exist for formal submissions to databases, but even informal reports via social media provide value by alerting other observers to changes or notable features worth targeting with more sophisticated equipment. The collective effort matters because astronomy increasingly operates through distributed networks. Professional facilities have limited telescope time allocated across many research programs. They conduct targeted observations at specific times using specialized instruments. Amateurs provide continuous monitoring, geographic diversity ensuring someone observes during time periods when professional facilities aren't scheduled, and rapid response to unexpected events like sudden brightness changes or outbursts. For 3i Atlas, combining professional spectroscopy, identifying molecular species with amateur photometry tracking, brightness evolution and global coverage, ensuring observations across all time zones, creates comprehensive dataset impossible for either group to achieve alone. Your observation, your measurement, your contribution becomes part of permanent record documenting this interstellar visitor's passage, data that future researchers will analyze when studying how comets from other stellar systems behave when they encounter our Sun. Step back from technical details about spectroscopy and photometry and observing techniques. Step back from specific questions about whether 3i Atlas turns blue during November observations. Consider the larger context, the deeper implications of why these observations matter, beyond documenting one comet's colour during one period of its orbit. What's really at stake during November 12th observations isn't just characterising 3i Atlas. It's building humanity's understanding of visitors from beyond our solar system, learning to recognise and interpret material from other stellar environments, establishing foundations for a field of astronomy that barely existed a decade ago and now represents one of the most exciting frontiers in solar system science. Historical perspective clarifies how recent this field is. For all of human history until 2017, every comet ever observed came from our solar system. Some comets visited from the distant Oort cloud, the spherical shell of icy bodies orbiting perhaps 1 light-year from the Sun, taking millions of years per orbit but still gravitationally bound to our star. Others came from the Kuiper belt beyond Neptune, completing orbits in decades or centuries. All originated here, formed from the same solar nebula that produced the Sun and planets 4.6 billion years ago. Their compositions reflected solar system chemistry. Their orbits were bound, elliptical paths that would bring them back eventually, even if their periods stretched across geological timescales. October 2017 changed everything. Pan-STARRS survey telescopes in Hawaii detected an object moving through the inner solar system on a trajectory that couldn't be reconciled with bound orbit. The hyperbolic path indicated speed exceeding solar system escape velocity. This object, designated Wana Oumuamua, was passing through a visitor from interstellar space, not a permanent resident of our solar system. Its discovery represented humanity's first confirmed detection of an interstellar object, the first time we recognize that material from other stellar systems regularly enters our cosmic neighborhood. The astronomy community realized immediately that Oumuamua couldn't be unique, that countless similar objects must pass through the solar system constantly, and that detecting them required only sufficient survey capability and recognizing their distinctive characteristics. 2 years later, Borisov confirmed the prediction. Amateur astronomer Gennady Borisov discovered a comet exhibiting obvious cometary activity coma, and tail clearly visible, but following hyperbolic trajectory, indicating interstellar origin. Unlike Oumuamua, which showed no obvious activity and might have been asteroidal in composition, Borisov was unambiguously cometary, actively sublimating volatiles as it approached the Sun. Spectroscopic observations documented its composition, revealing the carbon-rich signature this script has discussed extensively. 2i Borisov provided the first detailed compositional analysis of an interstellar comet, establishing baseline for comparison to solar system comets, and creating expectations for what future interstellar visitors might reveal about their formation environments. Now, 3i Atlas represents the third confirmed interstellar visitor, discovered in 2024 and reaching perihelion in late October 2025. Each of these objects contributes unique information, because they're independent samples from potentially different stellar systems, different formation epochs, different galactic regions. Studying multiple interstellar visitors allows pattern recognition. Are they compositionally similar, suggesting common formation conditions, or diverse, indicating they originate from varied environments? Do they share structural properties like nucleus size and density, or vary widely? What can their dynamics, how they move, how they respond to planetary gravitational perturbations tell us about their origins and histories? These questions matter profoundly for understanding planetary system formation beyond our solar system. We've discovered thousands of exoplanets through indirect detection methods like transits and radial velocity measurements. But these techniques reveal only basic properties like orbital parameters, mass, and in some cases atmospheric composition. We can't yet sample exoplanetary material directly. But interstellar comets are different. They're physical samples from other stellar systems that come to us, that we can study in detail using the full range of observational techniques applicable to solar system objects. They're messengers carrying information about the protoplanetary disks where they formed, about the chemistry of those disks, about the processes that built planets and smaller bodies in environments potentially very different from our solar nebula. What astronomers are trying to determine through observations like those planned for November 12th extends beyond individual object characterization. The research program encompasses questions about galactic chemistry and stellar system diversity. Are carbon-rich stellar formation environments common or rare? If multiple interstellar visitors show similar carbon enrichment, it suggests carbon-rich protoplanetary disks might be typical for certain classes of stars, perhaps those forming in specific galactic environments or during specific cosmic epochs. Conversely, if interstellar visitors show diverse compositions, it indicates stellar systems span a wide range of chemistries, making each visitor precious for sampling that diversity. The galactic history connection is particularly profound. Carbon abundance in the interstellar medium has evolved over cosmic time as successive generations of stars produce carbon through helium fusion and eject it through stellar winds and supernovae. Young galaxies early in cosmic history had low carbon abundance because insufficient time had elapsed for stellar nucleosynthesis to enrich the interstellar medium. Later epochs saw increasing carbon as more stars lived and died, cycling material through stellar interiors where fusion converted hydrogen and helium to heavier elements. If interstellar comets carry carbon-rich composition, their carbon-to-oxygen ratios and carbon isotope ratios potentially constrain when and where they formed in galactic history. An ancient comet from the thick disk might show different carbon chemistry than a young comet from the thin disk, encoding information about galactic chemical evolution in its composition. Thermal processing studies constitute another research area, advanced by post-perihelion observations. When an interstellar comet approaches the Sun, it experiences heating conditions that may differ from anything it encountered during formation or interstellar cruise. Most interstellar comets probably formed at distances from their host stars, comparable to where Kuiper belt objects formed in our solar system, cold environments where volatiles condense efficiently. After ejection from their birth systems, they spent potentially billions of years in interstellar space, at temperatures barely above cosmic microwave background, experiencing cosmic ray irradiation and interstellar UV exposure but no significant heating. Then they enter the inner solar system, suddenly experiencing temperatures hundreds of Kelvin higher than their entire previous existence. How does pristine interstellar material respond to this sudden heating? Do complex organic molecules decompose? And if so, what fragments result? Do subsurface layers preserve pristine composition while surfaces modify, creating stratification detectable through changing emission spectra? Does thermal stress fracture nucleus structure, exposing fresh material? November observations of 3I Atlas contribute to understanding these thermal evolution questions, testing models of how cometary ices and organics respond to solar heating, validating assumptions used throughout planetary science about comet thermal behavior. The pedagogical value shouldn't be understated either. Studying interstellar visitors teaches techniques and develops understanding applicable to solar system comets. Spectroscopic methods refined for interstellar object characterization improve capability for studying comets from the Oort cloud or Kuiper belt. Photometric monitoring strategies developed for tracking interstellar visitors during their brief passage through the inner solar system enhance general cometary science. The excitement generated by interstellar visitors attracts new researchers to cometary science, expands funding for surveys that discover these objects, develops infrastructure both instrumental and organizational that benefits broader planetary astronomy. For the public, interstellar visitors represent accessible cosmic connection. Understanding that objects from other star systems pass through our solar system, that we can observe them with backyard telescopes, that their compositions tell stories about distant stellar environments, this creates engagement with astronomy in ways that abstract exoplanet studies or distant galaxy observations sometimes don't achieve. You can point a telescope at an interstellar comet. You can see photons that travelled from another stellar system, reflected off a comet that formed there billions of years ago, crossed light years of interstellar space, and arrived at your eye after entering our solar system. That tangible connection, that direct observation of material from beyond, resonates emotionally and intellectually in ways that matter for sustaining public interest in space science and astronomy. November 12th, observations of 3i Atlas contribute to all these dimensions: individual object characterization, comparative studies building understanding of interstellar visitor diversity, galactic chemistry constraints, thermal evolution modeling, technique development, public engagement. The specific question of whether blue coloration appears, while interesting and scientifically valuable, represents one thread in a larger tapestry of research questions surrounding interstellar objects. Whether blue appears or not, the observations advance multiple research goals. The data collected during this narrow window, when post-perihelion evolution is most dynamic, and viewing geometry finally permits observation, after conjunction will feed into analyses that continue for months, papers that will be published documenting findings, databases that will preserve measurements for future researchers to mine when asking questions we haven't yet formulated. This is what makes November 12 genuinely significant rather than hyped for dramatic effect. The observations represent real science addressing real questions about our galaxy's chemical diversity and stellar system formation. They contribute to humanity's expanding understanding of the cosmos beyond our solar system, using visitors that come to us carrying information we cannot yet access through any other means. And they happen now, during a brief window determined by orbital mechanics and observational geometry, requiring coordination and effort from observers worldwide who collectively create understanding impossible for any individual or institution to achieve alone. That collaborative dimension, that democratization of cosmic discovery, makes this moment in late 2025 special, regardless of what specific results emerge from November observations, because the process itself, the method of studying these visitors, represents astronomy working as it should, rigorously, collaboratively, openly, pursuing understanding through careful observation and thoughtful analysis. Before continuing further, pause for essential intellectual honesty about everything this script has discussed regarding post-perihelion observations and potential blue coloration in 3i Atlas. Everything presented the spectroscopic expectations, the carbon chemistry interpretations, the observational preparations, the scientific implications rests on conditional foundation. This is speculation grounded in precedent and theory, not confirmation based on completed observation. The distinction between preparation and prediction matters enormously for understanding how science actually works, and for avoiding the pattern where public communication creates inflated expectations that actual results then disappoint when reality turns out more complex or different than simplified narratives suggested. Here's what is absolutely confirmed as of October 31st, 2025. Facts documented through multiple independent observations and not subject to uncertainty beyond normal measurement error. 3i Atlas reached perihelion on October 29th at precisely 11:47 UTC, approaching to 1.356 astronomical units from the Sun. The comet survived perihelion intact without fragmenting or disrupting, confirmed through October 30th observations that detected continued coma activity and tail structure consistent with a single intact nucleus. Pre-perihelion spectroscopy through late October clearly identified carbon dioxide, water ice, and nickel emission in the coma, along with weak but detectable diatomic carbon bands indicating C2 presence at low levels. Visual. Observations describe the coma as yellow-white dominated by dust scattering, typical for comets at that activity level and distance. These statements reflect confirmed measurements, recorded in observational databases, analysed by multiple research groups, and representing established facts about the comet's state through October 30th. Now contrast with what this script has extensively discussed, but which remains unconfirmed speculation. That 3i Atlas might show enhanced blue coloration in November observations after emerging from conjunction. This is possible. It's based on reasonable scientific expectations. Precedent exists from 2i Borisov, which did show carbon-rich composition and blue emission. Theoretical models suggest perihelion heating could release subsurface carbon-rich material or thermally decompose organics, creating carbon-bearing fragments that would produce blue emission. The weak C2 detection per perihelion indicates precursor chemistry exists. All these factors create plausible expectation that blue might appear post-perihelion. But plausible expectation is not confirmation. It's hypothesis awaiting test. November observations will perform that test, and only after those observations occur and data gets analysed will anyone know whether the hypothesis is supported or refuted. What if blue doesn't appear? This outcome would be completely scientifically valid and valuable. Absence of enhanced blue emission would indicate that perihelion heating didn't significantly increase carbon-rich species production, that subsurface layers accessible to thermal processing don't contain high carbon abundances, that 3I Atlas's composition differs from 2I Borisov's carbon-rich signature. Scientifically, discovering compositional diversity among interstellar visitors is important. It tells us that not all comets from other stellar systems share the same formation environment characteristics, that stellar system chemistry varies enough to produce detectable differences in ejected comets, that each interstellar visitor must be studied individually rather than assumed to match previous examples. No blue would not indicate observation failure. The observational program is designed to detect whatever composition actually exists, not to confirm predetermined outcome. If the comet shows no blue enhancement, spectroscopy will still identify what molecules dominate the emission spectrum, perhaps enhanced CO2, perhaps strengthened water ice features, perhaps continued dust dominance. That information is valuable. It characterizes 3I Atlas's actual composition, contributing to the growing dataset of interstellar visitor properties. Photometry will track brightness evolution whether or not color shifts toward blue, documenting activity patterns and sublimation rates that constrain models of nucleus composition and structure. Morphological monitoring will reveal coma and tail changes showing how the comet responds to decreasing solar heating as it recedes from perihelion. This bears repeating because it's fundamental to scientific thinking. The value of November observations lies in determining what actually is, not in confirming what we expect might be. Science advances through observation-based reality checking of theoretical predictions. When observations match predictions, confidence in underlying theory increases. When observations contradict predictions, theory requires revision or replacement, and that revision represents scientific progress by eliminating incorrect models and forcing development of better explanations. Either outcome advances understanding. Research quality depends on accurate measurement and honest interpretation, not on confirming hoped-for results. The language used throughout this script reflects this conditional stance, though it's worth making explicit. Phrases like may show, could reveal, might indicate, astronomers are watching for, expectations based on, if blue appears, all this conditional phrasing intentionally avoids claiming certainty about outcomes not yet observed. This isn't hedging or lack of confidence. It's epistemic humility, recognizing that nature determines outcomes, and our role is to observe and interpret accurately, not to predict with false confidence. Scientific communication sometimes struggles with this balance, wanting to sound authoritative while remaining honest about uncertainties, wanting to build interest without overpromising results. Preparedness versus prediction captures the distinction clearly. Astronomers are prepared to observe blue emission if it occurs. Instruments capable of detecting it are scheduled. Observation protocols specify how to measure it. Analysis methods exist for interpreting blue emission data. This preparation doesn't predict blue will occur. It ensures that if blue does occur, it won't be missed due to inadequate preparation. Simultaneously, astronomers are prepared for blue. Not occurring baseline comparisons will work, regardless of whether composition changed. Spectroscopy identifies whatever emission lines are present. Photometry quantifies actual colors independent of expectations. The observational program is robust to multiple possible outcomes, precisely because good science designs observations to answer questions rather than confirm predetermined answers. Intellectual rigor in astronomy demands maintaining this openness to multiple possibilities while rigorously testing through observation. Prejudging outcomes represents poor science. Designing observations that could only confirm one expected result, while missing alternative possibilities, is methodologically flawed. The November observation program for 3I Atlas exemplifies good practice broad spectroscopic coverage to detect whatever molecular species are present, multi-wavelength photometry to quantify actual colors, temporal monitoring to track evolution, coordination among observers to ensure comprehensive data collection. Whatever the comet actually shows, this program will document it accurately, and subsequent analysis will extract understanding from those measurements. So as November 1st arrives and observations begin, remember that everything discussed about potential blue coloration is hypothesis being tested, not fact being confirmed. The comet will show what it shows. Instruments will record that reality. Analysts will interpret measurements carefully, checking for instrumental artifacts and systematic errors, comparing results across different observers and facilities to verify consistency, and eventually reaching conclusions about what the data actually reveals about 3I Atlas's post-perihelion composition. That process takes time, data collection continues over days, preliminary analysis over weeks, peer review over months. Confidence in conclusions builds gradually as independent checks confirm findings and alternative explanations get eliminated. This timeline reflects how good science actually works, not dramatically with instant revelations, but methodically through careful accumulation of evidence and rigorous testing of interpretations. November the 12th represents the beginning of observation, not the final answer. Excitement about what might be discovered should coexist with patience about how discovery actually happens, and intellectual honesty about what remains uncertain until observation confirms it. The process is what matters: observation testing theory, data determining conclusions, reality having final authority over human expectations. That's science working properly, and November observations of 3I Atlas will exemplify that process regardless of whether blue emission appears or the comet reveals different chemistry than speculative expectation suggested. Understanding when events occur and what they mean organizes the narrative of 3I Atlas's passage through perihelion and subsequent observation into coherent structure. The timeline extends from the present moment in late October through coming months as observation transitions to analysis and eventually to publication of findings in peer-reviewed literature that becomes permanent scientific record. Each phase serves specific purpose in the process of converting raw observations into validated understanding, and recognizing how these phases connect creates realistic expectations about when different types of information become available and how confidence in conclusions builds over time. October 31st, 2025 represents now as this script is written and initial viewers encounter it. This is the preparation phase. Perihelion occurred 48 hours ago on October 29th. The comet survived intact as confirmed by October 30th observations. Solar conjunction continues blocking ground-based observation from Earth, forcing astronomers to wait for improved geometry. But this waiting isn't passive professional observatories, finalized scheduling for imminent observations, amateur networks, coordinate through online forums and social media to organize distributed observations. Prediction ephemerides get updated with latest orbital determinations. Finder charts get published showing where to locate the comet once observable. Analysis software gets prepared for processing incoming data. Everything stands ready for the observation window opening. November 1st and 2nd mark the critical observation window discussed extensively throughout this script. Solar elongation increases sufficiently that ground-based telescopes can observe the comet emerging from conjunction. Professional spectrographs obtain first post-perihelion spectroscopy with good signal-to-noise ratio since before perihelion, measuring emission lines and molecular bands that reveal composition. Amateur photometrists collect brightness measurements through multiple filters, quantifying colors and tracking activity. Visual observers report qualitative descriptions of appearance. Global coordination ensures continuous coverage across time zones. This is data collection phase where hypothesis testing begins through empirical observation, where reality starts determining what actually exists rather than what theory suggested might exist. November 3rd brings Venus flyby, a gravitational dynamics event rather than compositional observation. The comet passes Venus at approximately 0.65 astronomical units distance closer than it passed Earth, though Earth's passage already occurred weeks earlier during October. Venus's gravity creates small perturbation to the comet's trajectory, measurable through precise astrometry and useful for refining orbit determination and testing gravitational models. Additionally, Venus provides bright reference point in the sky near the comet's position, helping amateur observers locate the comet more easily and potentially enabling observations from urban locations where Venus's brightness allows initial sky location determination before searching for the much fainter comet nearby. November 4th through 7th represents preliminary analysis phase. Data collected during November 12th, observations gets compiled. observers upload measurements to coordination databases. Research groups begin analyzing spectroscopy to identify emission lines and measure line strengths. Photometric data gets calibrated and color indices calculated. Preliminary findings start circulating through informal channels, email lists, social media posts, conference presentations if any meetings coincide with this timing. Media coverage likely begins if interesting results emerge, though responsible science communicators emphasize preliminary nature of findings pending careful analysis and peer review. This phase converts raw observations into initial interpretations while recognizing those interpretations require verification. November 8th through 15th involves data consolidation. Spectroscopic measurements from multiple observatories get compared to verify consistency and identify any systematic differences requiring explanation. Photometric measurements from many amateur observers get aggregated. Statistical analysis identifying outliers and calculating mean values with uncertainties. Compositional interpretation advances based on spectroscopic evidence are carbon species enhanced. Do color indices indicate blue shift? How do post-perihelion measurements compare to pre-perihelion baseline? Discussions among research groups refine interpretations and identify additional observations needed to resolve ambiguities. Plans for formal publication begin forming as key findings become clear. Late November through mid-December represents submission phase for scientific papers. Researchers write manuscripts analyzing November observations, comparing to previous interstellar visitors, discussing implications for stellar system chemistry and cometary thermal evolution. These papers get submitted to peer-reviewed journals Nature and Science for high-impact broad audience results, Astrophysical Journal for detailed spectroscopic analysis, Icarus for solar system and cometary science, Astronomy and Astrophysics for European perspective. Submission triggers peer review process, where anonymous expert reviewers evaluate methods, check calculations, assess whether conclusions follow from data, and recommend publication, revision, or rejection. This typically requires 4 to 8 weeks, extending into early 2026 before papers emerge from review. December 19th marks Earth's closest approach when the comet reaches 1.80 astronomical units distance from Earth, about 270 million kilometers, still quite distant but geometrically optimal for observation. This represents final extended observation window, when the comet remains bright enough for detailed study. Amateur observers have best opportunity for visual and photographic observations during this period. Professional facilities may schedule additional spectroscopy for comparison to earlier measurements, tracking how composition evolves as the comet continues receding from the Sun and cooling progresses. After this closest approach, the comet begins fading as increasing distance reduces both intrinsic brightness from declining activity and apparent brightness from growing distance, making observations progressively more challenging. January through February 2026 involves peer review of submitted papers and continued analysis. Additional observations may continue from professional facilities, tracking the comet's fade and characterizing long-term evolution. Amateur observations taper as the object becomes fainter and less accessible to modest equipment. Citizen science contributions transition from active observation to data analysis. Amateur spectroscopists processing collected spectra, photometrists refining measurements, imagers creating time-lapse sequences showing morphological changes. The focus shifts from acquiring new data to extracting maximum understanding from data already collected, ensuring thorough analysis before formal publication. March 16, 2026 brings Jupiter flyby at 0.36 AU distance, the comet's final encounter with major planet before exiting the inner solar system. Jupiter's substantial mass creates more significant gravitational perturbation than earlier planetary passages, measurably altering the trajectory and potentially slightly changing the hyperbolic excess velocity with which the comet eventually exits the solar system. This represents last major observational milestone. Professional observatories may schedule final spectroscopy and imaging, documenting the comet's state approximately 5 months after perihelion, when activity has declined significantly, and surface layers modified by solar heating have largely sublimated away, possibly exposing deeper layers for spectroscopic study. April through May 2026 likely sees publication of peer-reviewed papers as review processes complete and revised manuscripts gain acceptance. Published papers present comprehensive analysis of 3I Atlas's composition, thermal evolution, comparison to other interstellar visitors, and implications for understanding stellar system chemistry. These publications become authoritative references that future researchers cite when studying interstellar objects. The findings enter textbooks slowly, as textbook publication cycles span years, but eventually the 3I Atlas observations become part of standard astronomical knowledge taught to students learning about comets and interstellar visitors. June 2026 onward represents the fading phase as the comet recedes to outer solar system distances where solar heating becomes negligible and activity ceases. The object becomes too faint for amateur observation and challenging even for professional facilities. Tracking continues with largest telescopes and most sensitive instruments, measuring how fast activity declines and how far from the Sun the comet remains detectable. Eventually, perhaps in late 2026 or 2027, the comet fades below detection thresholds of even the most capable instruments, disappearing from observation as it exits the solar system on its hyperbolic trajectory, returning to interstellar space carrying whatever modifications solar heating produced during its brief passage through the inner solar system. This timeline matters because it shows that astronomy is process extended over time, not instant revelation. November observations are exciting because they begin empirical testing of expectations, but they're the start of months-long progression from data collection through analysis to peer-reviewed publication. Understanding this timeline creates appropriate expectations. Initial findings emerge within days, preliminary interpretations within weeks, published validated conclusions within months. Each phase adds rigor and confidence. The process ensures conclusions rest on solid evidential foundation rather than premature interpretation of incomplete data. And this methodical progression, while requiring patience, produces reliable knowledge that withstands scrutiny and becomes foundation for future research, building progressively deeper understanding of interstellar visitors and the stellar systems from which they originate. After exploring spectroscopy, thermal evolution, observation techniques, and publication timelines, step back to fundamental question. Why does any of this matter to you specifically, the person watching this, the individual who may never professionally study astronomy, but nonetheless encounters this information about an interstellar comet potentially turning blue after perihelion? What makes these November observations relevant beyond the small community of professional astronomers and dedicated amateur observers who will conduct the measurements? The answer operates on multiple levels: practical engagement opportunity, connection to cosmic context, participation in knowledge creation, and ultimately philosophical significance about humanity's expanding awareness of the galaxy we inhabit. The most immediate answer is participation opportunity. Right now, in late October and early November 2025, you live during a moment when an object from another star system passes through our solar system, close enough to observe with amateur equipment, and during a phase when its evolution might reveal profound information about its composition and origin. This is rare. Only 3 interstellar visitors have been confirmed ever, and only 2 were cometary objects bright enough and discovered early enough for extensive observation. The next might arrive in months, years, or decades, depending on survey detection capabilities and random orbital geometries. This November represents a specific window when anyone with telescope and clear skies can observe an interstellar visitor during scientifically interesting evolution. You can actually do this. November 1st onward, if you access telescope equipment, whether personal ownership or through astronomy club or public observatory, you can point that instrument toward the coordinates where 3I Atlas appears and see photons that travelled from material formed in another stellar system. Those photons reflected off or were emitted by atoms and molecules that condensed from a protoplanetary disk around a star that isn't our Sun, in a region of the galaxy distant enough that we'll likely never travel there, under chemical conditions potentially different from our solar nebula. The light entering your eye or camera sensor carries information about that distant origin, and by observing carefully and reporting measurements to coordination databases, you contribute to humanity's collective effort to understand these cosmic visitors. That's not passive consumption of information, it's active participation in frontier science. The democratization of astronomical discovery has transformed over recent decades. Previous generations could look at celestial objects but couldn't, meaningfully contribute to professional research, the equipment gap between amateur and professional capabilities was too large, and coordination mechanisms didn't exist for aggregating amateur observations into useful datasets. Now, amateur equipment has reached quality enabling serious measurements. Digital imaging and photometry have become accessible through affordable cameras and free software, and internet coordination platforms enable global networks to organize observations and share data instantly. Professional astronomers explicitly recognize amateur contributions as valuable, incorporating amateur photometry and spectroscopy into research programs, and acknowledging amateur observers in published papers. For 3i Atlas specifically, your observation on November 1st or any subsequent date when you manage to detect the comet adds one more data point to the record documenting this interstellar visitor. If you measure brightness, your measurement combines with hundreds of others to track activity evolution with temporal resolution impossible for any single observer. If you notice color characteristics, your report adds to accumulated evidence about whether blue emission appears. If you capture images, your photographs document morphology from your specific viewing geometry and time. The contribution might seem small individually, but collectively amateur observations create comprehensive dataset that professional spectroscopy alone cannot achieve due to limited telescope time allocation and geographic constraints of fixed observatories. Beyond practical participation, there's cognitive and emotional dimension to observing interstellar visitors. Understanding that material from beyond our solar system regularly passes through our cosmic neighborhood fundamentally changes perspective on our place in the galaxy. We're not isolated, the solar system exists within galactic environment, where stellar systems exchange material through gravitational perturbations, ejecting comets and asteroids into interstellar space, where those ejected objects drift on trajectories that occasionally intersect other stellar systems including ours. This material exchange means we can study other stellar systems without traveling to them, receiving samples delivered by gravitational dynamics operating over galactic scales. The frequency of interstellar visitors remains uncertain, but appears substantial. Before Oumuamua's discovery, estimates varied wildly because no detections existed to constrain models. Post-2017, statistical analysis suggests perhaps dozens to hundreds of interstellar objects might pass through the inner solar system annually, though most remain too faint or pass too quickly for current surveys to detect. As observational capabilities improve through projects like the Vera Rubin Observatory, beginning full operations in coming years, detection rates will likely increase dramatically, potentially finding multiple interstellar visitors monthly. We're entering an era when studying material from other stellar systems transitions from rare opportunity to regular research program, building catalogues of interstellar object properties that reveal patterns about galactic stellar system diversity. What does this mean philosophically? It means we're developing capability to characterize stellar systems across the galaxy through the material they eject. Spectroscopy of interstellar comets reveals formation, environment chemistry, carbon-to-oxygen ratios, isotope ratios, noble gas abundances, dust grain properties. All these characteristics encode information about the protoplanetary disk where each visitor formed. Compile enough examples, and patterns emerge connecting composition to stellar system properties. Maybe carbon-rich comets correlate with specific spectral types of host stars. Maybe compositional diversity reflects galactic location or stellar age. Building this understanding creates taxonomy of stellar formation environments, without requiring direct observation of those environments, using the samples they send us as proxies for studying environments too distant for current instruments to characterize directly. There's also existential dimension to recognizing that we share galaxy with countless other stellar systems, some of which likely host planets, some of which might harbor life. Interstellar visitors remind us that space between stars isn't empty void, but dynamic environment, where material moves between systems. Panspermia hypotheses suggest life itself might spread between stellar systems through exactly these kinds of transfers, microorganisms embedded in ejected comets surviving interstellar transit, and potentially seeding life on planets in recipient systems. While highly speculative and unproven, the concept illustrates how interstellar material exchange creates potential connections between otherwise isolated stellar systems, making galactic community more interconnected than simple distance measurements suggest. For you personally, understanding 3i Atlas observations connects you to this emerging galactic awareness. When astronomers determine whether the comet shows blue emission, indicating carbon-rich composition, when they measure isotope ratios constraining formation conditions, when they track how the comet responds to solar heating revealing material properties, you're witnessing humanity develop new capability for characterizing stellar systems beyond our own. This is exploration not by traveling to distant systems, but by studying the samples they send us. And you can participate directly by observing, or indirectly by understanding, what observations reveal and why that matters for cosmic perspective. The privilege of living during this specific historical moment deserves recognition. Previous generations wondered about stars and planets, but couldn't detect exoplanets or interstellar visitors. The technology didn't exist. Future generations will have extensive catalogues of interstellar objects and routine characterization procedures, perhaps even dedicated missions to intercept and sample them as they pass through the solar system. But right now, in 2025, humanity stands at the beginning of this capability, detecting first examples, developing methods, experiencing the excitement of frontier discovery where each new interstellar visitor teaches something unexpected. You're witnessing this transition, and if you engage by observing or even by understanding what observations mean, you're participating in humanity's expanding awareness of the galactic environment we inhabit. November 12th, observations of 3i Atlas matter, because they contribute to this larger program characterizing interstellar visitors, building understanding of stellar system diversity, developing techniques for studying material from beyond our solar system, engaging global community of professional and amateur astronomers in coordinated discovery. Whether blue emission appears or not, whether the comet reveals carbon-rich composition or maintains solar system-like chemistry, the observations advance collective understanding. And that advancement, that incremental but real progress in human knowledge about the cosmos, justifies attention and participation from anyone curious about the universe beyond Earth, about the diversity of stellar systems across the galaxy, about humanity's growing capability to study environments we cannot directly visit by carefully analyzing the messengers those environments occasionally send our direction, carrying encoded information waiting to be decoded through patient observation and thoughtful analysis by astronomers distributed across our planet, working together to understand visitors from the stars.